Imagine this. Deep in the heart of a distant galaxy, an impossibly dense, invisible monster waits in silence. Nothing escapes its pull. Not planets, not light, not even time as we know it. It's the ultimate trap, the place where physics breaks down and reality itself begins to blur. It's a black hole. And now, imagine this. We destroy it. What happens next? To answer that question, we have to journey to the very edge of what we know and a little beyond. Because black holes aren't just mysterious objects drifting in space. They're cosmic engines of gravity, forged in the most violent events in the universe, and perhaps connected to its deepest secrets. But before we destroy one, however hypothetically, let's understand what we're up against. A black hole is not a thing in the way you might imagine. It's not a planet or a star you can land on or poke with a stick. It's space, twisted beyond recognition. When a massive star dies, its core collapses under its own gravity. If enough mass is compressed tightly enough, it warps space-time so severely that it creates a gravitational prison. The result? A region where the escape velocity exceeds the speed of light. That boundary is called the event horizon. Once something crosses it, it's gone forever, at least from the perspective of the outside universe. Now let's say you wanted to destroy this black hole. First question, how? You can't blow it up with missiles or laser beams. There's nothing solid to hit. The mass is concentrated in a single point called a singularity, a place where density becomes infinite and physics as we know it breaks down. So any conventional means are immediately off the table. But let's keep going. Say you're some ultra-advanced civilization, type II on the Kardashev scale, with technology that lets you manipulate gravity, energy, even space-time itself. Could you destroy a black hole then? In theory, yes, but there are different ways to do it, and each has its own bizarre consequences. Let's start with the slowest method first, Hawking radiation. In 1974, Stephen Hawking proposed something wild, that black holes aren't truly black. Due to quantum effects near the event horizon, they slowly emit particles, losing mass over time. This process is called Hawking radiation, and it means black holes can, in theory, evaporate. For a stellar mass black hole, though, this takes longer than the current age of the universe. We're talking trillions upon trillions of years. What if we wait long enough, that black hole will shrink and heat up until it releases one final burst of energy and vanishes. So what happens when a black hole dies this way? In the final moment, the black hole explodes in a blinding flash of high-energy radiation. It's like a mini Big Bang, an enormous release of gamma rays and particles into the cosmos. The total energy unleashed is equal to all the mass the black hole ever contained, converted into pure energy by Einstein's famous equation, E equals mc². But this isn't destruction in the dramatic Star Wars sense. It's more like a long, cold candle finally burning out, a cosmic exhale. And when it's gone, all that remains is a ghost of gravity and a serious mystery about where all the information went. More on that in a bit. Now let's try something more intense. Let's say you throw antimatter into the black hole. Matter and antimatter annihilate on contact, releasing energy. So maybe, just maybe, this could destabilize the black hole? Not quite. The problem is that once the antimatter crosses the event horizon, it becomes part of the black hole. Matter-antimatter, it doesn't matter. The black hole doesn't care. It just grows more massive. You're feeding the beast, not starving it. So what if we go even bigger? What if we create a destructive gravitational wave, a ripple in space-time powerful enough to tear the black hole apart? Here we start to reach the limits of what's even theoretically possible. You'd need to manipulate gravitational forces on a scale equivalent to merging black holes, a process that releases more energy in a fraction of a second than all the stars in the universe combined. Even then, you're not really destroying the black hole. You're merging it with another or creating new ones. The end result is still a black hole. But there's one more option, and it's the strangest. What if we could somehow reverse the collapse? What if we could turn the black hole inside out? To do that, you'd have to apply some form of negative energy or exotic matter to counteract gravity's pull. This is the stuff of hypothetical constructs like wormholes or white holes. The time-reversed version of black holes that spew matter out instead of sucking it in. No one knows if white holes actually exist, but if they did, And if you could force a black hole to transform into one, you get an incredible release of energy and information. Everything that ever fell into the black hole could, in theory, come bursting back out. Think about that. Stars, planets, data, even light itself, scattered across eons, could reappear in a final, chaotic release. But here's the kicker. We have no idea what that would look like. Would it be a massive explosion? A quiet unraveling? Would it rip a hole in space-time? Or would it simply violate every known law of physics? This brings us to the biggest mystery of all, the black hole information paradox. According to quantum mechanics, information can't be destroyed. If you burn a book, the atoms rearrange, but the information is still there, at least in principle. But if you throw that book into a black hole, it seems to disappear forever. And that terrifies physicists. Because if information truly vanishes inside a black hole, then everything we know about quantum theory and the fundamental workings of the universe might be wrong. Some believe the information is stored in the event horizon itself, like a hologram. Others think it leaks out slowly through Hawking radiation. And a few propose that black holes are actually bridges to other universes, where the information still exists, just somewhere else. If we could destroy a black hole and watch what happens in that final moment, we might finally solve this mystery. We might glimpse the quantum structure of space-time, or see proof of extra dimensions, or even witness the birth of something new entirely. But here's the final twist. You can't really destroy a black hole in the traditional sense, because it's not a thing that breaks. It's a region of reality that bends, and when it's gone, either by evaporation or exotic collapse, it doesn't leave behind a crater or a mess. It leaves behind questions. Questions about space, time, gravity, and where everything goes when it falls beyond the veil. Because when you destroy a black hole, if such a thing is even possible, you're not just ending an object. You're poking at the very fabric of existence. And who knows what might poke back?